What is up, good people? This is Mr. Bergman here with section 5.5.2, roots and zeros, complex applications. So we're going to continue talking about roots and zeros, but today we're going to add our old friend I, the square root of -1. It's imaginary time. So let's go. First, let's do some review. Let's multiply some complex conjugates. What's a conjugate? Oh, well, it's two different numbers that are that have imaginary parts, and you just do it's like a plus bi and then a minus bi. You notice the only difference between these two things that we're multiplying, these two complex numbers, is that one is plus and one is minus. And when you multiply them together, this is what happens. You can FOIL. So the first term, 4 times 4 is 16. Outside term is 4 times -3i, which is minus 12i. The inside term is 3i times 4 is plus 12i. And then 3i times minus 3i is minus 9i squared. I squared, what is that? It's -1. So that's going to cancel out the subtraction. You just have, and then of course the middle two terms cancel each other. And then you just have 16 plus 9, which is 25. Let's do 2 minus I and 2 plus I. You multiply these together, you get 2 times 2, which is 4. Outside term is 2 times I is 2i. Inside term is minus I times 2, which is minus 2i. And then the last term, minus I plus I, is going to be minus I squared. And then, of course, I squared is -1, so the minus and the negative cancel out. And you got 4 plus 1, which is 5. Let's do another one. These are also conjugates, even though there's no real portion to this number. It's just minus 4i times positive 4i. It's going to be minus or negative 16i squared, which turns into 16 because the I squared is -1. I squared is -1. I squared is -1. So the big idea here is the complex conjugates theorem. I'm going to start with a big idea and show you how to use it. Here's the big idea for today. If a complex number, like one of these, 4 plus 3i or 2 minus I, or in general, a plus bi, is a zero of a polynomial function, that means if you take a plus bi, whatever it is, and you put it in as an input to the polynomial function and you get as an output 0, with real coefficients, this polynomial function has real coefficients. Like every function we've worked with so far has had real coefficients. Like the a, b, and c term are all real numbers. They're not imaginary numbers. Then a minus bi is also going to be a 0. And that's why a minus bi and a plus bi are complex conjugates theorem. So if one of them is going to be a 0, then the other one is also a 0. That's what the theorem states. Here's how Alex tests us in that. Let's see. This is how Alex tests us. So it might say alex.com. We might say find a polynomial of degree 4 with real coefficients and the following zeros. 3 that has a multiplicity of 2 and 1 minus I. Well, okay, so what it's basically saying is that this thing is going to have degree 4. That means it's going to have 4. The fundamental theorem of algebra says that if the degree is 4, then there's going to be 4 zeros. Well, the multiplicities, if you add up all the multiplicities, they're going to be 4. So 2 of them are going to be here with 3, and then one of them is going to be here, and then the other one is going to be complex, 1 minus I, 1 plus I. So you can basically say we've got all 4 of the zeros now. The big idea we just learned, complex conjugates theorem, says that if 1 minus I is a 0, then 1 plus I is also a 0. So we can actually write this out as f of x. We know what it is. It's going to be in factored form. It would be x minus 3 squared. Remember, 2 is indicating the multiplicity, and then we're going to do x minus the root in parentheses. Super important to make sure we have these parentheses here. X minus the root. X minus the root. Say it with me. X minus the root. And so what we've got next is a whole bunch of foiling. We need to get rid of the inner parentheses, so distribute the subtraction. This becomes x minus 1, and then the minus and the minus cancel and become plus I. Getting rid of these inner parentheses, we get x minus 1, and then minus I. We remember a minus b squared is going to be a squared minus 2ab plus b squared, and that's the formula that I remember in order to go from here to here. So now we basically have three things, and they've been the exponent has been taken care of, the inner parentheses have been taken care of, and now we just got to multiply them together. I'm actually going to multiply the second two terms, and then it doesn't matter which order. You could do, if this is term number one, factor number 1, factor number 2, factor number 3, you could multiply factor number 1 times factor number 2, get the result, and multiply by factor number 3. But I'm actually going to do factor 2 and 3 first, because I think there's going to be I think the i's will disappear because they came from complex conjugates. So, good old friend box method, this is going to be a 3 by 3 box. We've got x minus 1 plus I, x minus 1 plus I, and then x minus 1 minus I over here. X times x is x squared. X times minus 1 is minus x. X times I is ix. I'm going to write it alphabetically here, just so that it helps me cancel out terms. Negative 1 times x is negative x. Negative 1 times negative 1 is positive 1. Negative 1 times negative I is negative I. And then negative I times x is negative ix. Negative I times negative 1 is positive I. And then negative 1 times negative I times positive I is negative I squared, which, because I squared is negative 1, the two negatives cancel out and it's positive. Notice you're going to have a whole bunch of terms that cancel. And if you do this right at this stage of the game, because these factors came from complex conjugates, a plus bi, a minus bi, at this point, all the i's should drop out. If you've got x squared, fine. Minus x plus minus x is, negative x plus negative x is negative 2x. 1 plus 1 is 2, but all the others, the red terms cancel, the gray terms cancel, and we're just left with x squared minus 2x plus 2, which at this point is all the i's drop out, and now we have a 3 by 3 times a trinomial times a trinomial, and you can do another box. It's going to look like this: x squared 6x minus 6x plus 9, x squared minus 2x plus 2. You do all the multiplying, and you notice, I'll give you a little bit of time to copy it down. You notice that x squared times x squared is x to the 4th. X squared times negative 6x is negative 6x cubed. X squared times 9 is 9x squared. And then minus 2x times x squared is minus 2x cubed. Minus 2x times negative 6x. Negative 2x times negative 6x is positive 12x squared. Negative 2x times positive 9 is negative 18x. 2 times x squared is 2x squared. 2 times negative 6x is negative 12x, and 2 times 9 is 18. The blue terms combine. They're like terms. All the red terms are like terms. They also combine, and the gray terms as well. So when you rewrite the whole thing here, it's x to the 4th minus 8x cubed plus 12x squared minus 30x plus 18. This is the polynomial function. Let's check. Let's take a look at the original instructions. It says, find a polynomial f of x. This is a polynomial. You can see it right here. There's no parentheses. Of degree 4, the degree is 4 here, with real coefficients. All the coefficients, 1, negative 8, positive 23, negative 30, positive 18. They're all real numbers. There's no I. It's not like 30ix here or 23ix squared. No, they're all real numbers. They're real coefficients. And the following zeros. So if you wanted to, you could put 3, for example, in here for x, and you should get 0 out. You could even put 1 minus I. You could even put 1 plus I here. And I'll bet you if you graph this, then it'll indicate that when x equals 3, it not only will it be an x-intercept because it's a 0, but it will bounce off the x-axis. Boom! There it is! Oh, that's so cool. Check it out. This is x equals 3. It bounces off the x-axis. And I should have also noted this earlier. It doesn't cross the x-axis anywhere else. It only has one real root, so therefore it only has one x intercept. The other roots, the other potential x-intercepts are all complex, and they don't actually. There's no place for them on this graph, on this real number line. So that's fun. Let's see. Let's go back. All right. So next slide. Let's focus in on this. For the polynomial 3 is a 0. What is g of x in factored form? So here we notice that the degree is 3, so there's going to be 3 different zeros, and they give us only one of them. They want to know what the others are. Okay, so what we're going to do is we're going to divide. Kind of like saying if the number 30 is what are the factors of 30? What are the numbers that multiply up to 30? And one of those numbers is 2. You could say, well, okay, let's start, take 30 and divide it by 2, and you get 15. So then I got a factor of 15. And the answer would be 2, 3, and 5. Those are the factors of 30. Well, we can do the same thing with a polynomial. And in order to find, we're given the first one, and there's 2 more. Let's find the other 2. Let's find the other 2 factors. So let's actually divide. We've got 3 here. That means we know that x minus 3 is one of the factors. We're going to do some synthetic division. Let's see. Remember, we bring down. This is. Let's check for placeholders. We got 1x cubed negative 1x squared plus 4x minus 30. It seems like we have all the terms represented, so no placeholders necessary. Bring the 1 down here. 3 times 1 is 3, plus negative 1 is 2, times 3 is 6, plus 4 is 10, times 3 is 30, plus negative 30 is 0. And you know what? Did we expect this 0 to get here? Yeah, we did, because 3 is a 0. It's an input that will produce an output of 0. So this, if we don't get a 0 here, then you got to double check your work because something's wrong. But what we're left with is 1, 2, and 10, and this is what we're after here. If we wanted to, you could rewrite this polynomial as f of x is equal to x minus 3 from here. That's the one we know, and then the rest of it is 1x squared plus 2x plus 10. And then you've got lots of different tools at your disposal to continue to factor this. For example, but like what 2 numbers multiply up to 10 and also positive 10 and also add up to positive 2? No easy numbers, so you can use, for example, the quadratic formula. If we see a is 1, b is 2, and c is 10, and plug that into the quadratic formula, you know how to do that. It's gonna give you these 2 numbers. X is equal to negative 1 plus or minus 3i. Notice these are complex conjugates. The complex conjugate theorem states that if you can't just have negative 1 plus 3i, you have to have both negative 1 plus 3i and negative 1 minus 3i. So they're both going to be zeros as well. So if you want to write out the answer, it's not just going to be this. You can write it out as 3 different factors. X minus the root. X minus the root, the entire root. You have to see it's in parentheses here. X minus the entire root in parentheses. And so that's what helps us here. And that's the answer. You can type that in. Let's do a little warm-up. Oh, no, let's do write a polynomial function that could be represented by the following graph. And so here, what we got to take graphical information like x-intercepts and turn it into a polynomial. Well, here let's look at the x-intercepts. The x-intercepts are negative 4 and positive 1, and I want you to tell me what the third x-intercept is. If we notice another more graphical information is that they all of these x-intercepts cross the x-axis, and if that's true, then they're all going to have odd multiplicities. Another thing that's true is that it has, if we can see from the graph, that the y-intercept is going to be negative 8, and also this is going to be down. The end behavior is down, up. Those are the arrows. There's a down arrow here, and there's an up arrow here to indicate how it's leaving the window. So the down up odd end behavior indicates that it's going to be an odd degree and a positive leading coefficient. So taking all that together, you can write f of x, the x-intercepts tell us x minus the root, x minus the root, x minus the root here. And so we've written this out. What are the multiplicities going to be? They're all going to be odd, and then on top of that, they're all going to have, if you add them up, the total is going to be odd as well. So let's just start with 1, 1, and 1, because it seems like it might work. And then you can FOIL the first two to get x squared plus 6x plus 8, and then box method. I didn't show the work for that. X squared plus 6x plus 8. You draw another box times x minus 2, be like a 2 by 3 box, and then eventually you get this entire thing. Now, does it also satisfy all the other information? Y-intercept is negative 8. Yeah, right here. Well, from this minus 8 term. And then positive leading coefficient. Yep, we're good there. So I think everything is good. If this weren't, like, let's say for whatever reason we did the multiplication, we got negative 4, and we expected negative 8, then you could put a 2 out in front, like multiply the entire thing by 2, and that would adjust the y-intercept. Let's see, we already did that one. Okay, so as a warm-up, if we know that 30 is equal to 2 times 3 times something, what is that something? You got two options here. You could divide by 2 and then divide by 3, and you're left with the something. So 30 divided by 2 divided by 3 is 5. You could also just multiply the 2 times 3 together to get 6, and then divide that. So you could do 30 divided by parentheses 2 times 3, which is equal to 5. What I'm trying to say is both these methods are valid, and we can think about both of them as well. If you know that 42 is a number and it's got 3 factors, 2 of them are 2 times 3, you're trying to find the third one. Your two options are divide by 2 and then divide by 3, and you get 7. Or you could also take 42 and divide it by the product of these. 2 times 3 is 6. 42 divided by 6 is 7. The same thing works for polynomial factors. So in this problem, it says find all the other zeros of p of x, and that's x cubed plus 8x squared plus 25x plus 26, given that negative 3 plus 2i is a 0. Well, if the complex conjugate's theorem says that if negative 3 plus 2i is a 0, then its conjugate is also a 0. There are, like, I could think of 1, 2, 3, 4 different ways of doing this. We're going to divide. We could, if we wanted to, like here in our warm-up, we could multiply first and then divide the results, but I think we're just going to do multiple repeated division. So we'll start with that large polynomial and divide by a number, and then divide by another number to get the third factor. Sorry, divide by a factor to get the third factor. So what we do, we could multiply first and then divide the result, and you wouldn't be able to use synthetic division. You have to use polynomial long division. I can show you how to do that if you're really interested, but to keep the video short, I'm just going to do this. We're going to divide using synthetic division, and we're going to divide twice to get the third factor. So if 3 plus 2i is a 0, then, as I already said, negative 3 minus 2i is also a 0. So let's take our polynomial. The coefficients are 1, 8, 25, and 26. 1, 8, 25, and 26. And let's divide by our first 0 using synthetic division. And so negative 3 plus 2i. I know this might be the first time we're seeing a complex number out here, but we can do this. So what happens is, first thing we do, we proceed as normal. Bring down the 1, and then multiply by negative 3 plus 2i. You get negative 3 plus 2i. You add 8. The 2i is unaffected. It goes down here, but 8 plus negative 3 is 5. Then you have to multiply negative 3 plus 2i times 5 plus 2i. And what we do is we get negative 19 plus 4i. I'll show you the work over here. To keep the video short, I'm just going to say that when you FOIL, you're going to have to do a lot of complex conjugate foiling, but remember, the hardest part, I think, is remembering that I squared is negative 1. If you can do that, then maybe the other parts aren't too bad. You get negative 19 plus 4i. So what is 25 plus negative 19 plus 4i? Well, the 4i goes along for the ride. It's unaffected, but 25 plus negative 19 is 6. You got to do that again. Negative 3 plus 2i times 6 plus 4i. Foil that again. And here you can see when you foil it, you get negative 26. This is 8 plus 8. Remembering 8i squared is negative 8 plus negative 18 is negative 26. The middle terms cancel out. And we get 26 plus negative 26 is 0. Do we expect, wow, is that random chance? Should this be 0? Yes, we should expect this to be 0 because we are told that negative 3 plus 2i is a 0. If we don't get 0 here as an output, then we know something is wrong. As a remainder, sorry, this is a remainder, but the output, if the output is 0, then the remainder is also a 0. That's the remainder theorem. All right. We're using the complex conjugate theorem. We know if this is a 0, then this is also a 0. So we're going to go, we're going to divide the result. We're going to stack these. We took the big papa polynomial, we divided it by the first one. We got the mama polynomial right here. It's a little bit smaller. And then we're going to go negative 3 minus 2i. Bring down the 1. Multiply by negative 3 minus 2i is right here. 5 plus 2i, and notice plus 2i and minus 2i, they cancel. 5 minus 3 is 2. Multiply this here, we get negative 6 minus 4i, and notice plus 4i and minus 4i cancel, we get, and 6 and minus 6 cancel, we get 0. Should we expect that? Is that random? Does sometimes it not work? No, it should always be a remainder of 0, because negative 3 minus 2i is a 0. If the input is 0, then the output is the remainder, and we can see that it's going to be 0 right here. And then you might say, okay, well, the last one, you bring 1 down. You might not know what negative 2 is, but you bring 1 down and you have to multiply something by negative 2 to get this number right here. And so 2 times negative 2 is going to be 0 right here. 0, 0, 0. And here are the 3 factors: negative 3 plus or minus 2i and negative 2. So the big number that we're looking for is negative 2 here, and we found it. You could guess and check if you want, but the algebraic way to do it is to, what just happened? Is to divide using complex synthetic division twice. And you can, the fourth way, so you could guess and check the answer if you really wanted to. You could divide using complex synthetic division, repeated complex synthetic division, or you can multiply first. So you can multiply these conjugates together and then divide the result using polynomial long division. Or if you wanted to, you could graph it. If you have the access to a graph and graphing is not too difficult, then you could also graph it here. Remember, zeros and x-intercepts are very related. So there's the x-intercept is negative 2. Wow, that was chapter 5, and we've wrapped it up. It's been a wild ride, and I can't wait to show you what the project looks like, because it is also a lot of fun. Take care, and I'll see you in class. And I just wanted to say that my favorite thing to make my kids for breakfast is pancakes. It's just anytime there's a birthday party or celebration of some sort, we got pancakes for breakfast, and my kids love it. Take care, and I'll see you in class.